Okay, let's start our class. Before the class, just let me mention one thing that I heard. The USA University of South Alabama has sent everyone a survey about this class. Please take some time to finish the survey. And also for the final exam, so as you have received the email, so today is May 14th, and our last class will be on Thursday, May 16th, and I will release a take-home on final exam on Friday. So I'm thinking I will try to make it like in the morning of Friday. So I'm thinking how about we set the due time to be the end of Monday. If you like really practice in no matter the homework or like watch the videos, the most important thing is you need to code rather than just look at me code it, and then when you code this stuff, it's easy to make some mistakes. This is also the reason why I insist to show you the coding process, even if I made a lot of mistakes in class, because I mean, watch another person to code and you code by yourself, it will be really different. Okay, so I'm thinking to make it to be maybe Monday due, and so you will have the weekend plus one more day. If you're familiar with that, I believe it will be really fast because anyway, you will see it. Again, this class, there's no ABCD, there's only pass and fail. So I believe if you submitted the homework and then finish the final exam, I believe it's pretty simple to pass it. Okay, so then let me start our class. So in the last class, we mentioned the clustering. Let me give a very quick review. So first of all, what is unsupervised learning? Unsupervised learning, there's no teacher or there's no label. So a very typical thing is a pattern recognition. So for example, here, like this is supervised learning in which we have the labels class 1, 2, 3. And here is unsupervised learning. You can see all the data are in dark, meaning that there's no no labels. You need to find that this is one pattern. Oh, sorry about it. Let me have to annotate. Zoom interesting. Required to have the annotate, otherwise it won't be shown. It asks you to find the 3 patterns by yourself. That is the unsupervised learning, not something like here. I already gave you these labels. Here you don't have labels. Okay, so for this clustering is to group data objects into clusters such that objects in the same cluster are more similar to each other than in other clusters. And that's the reason why if, say, I ask you to give me 3 clusters, I would prefer to be like this. Cluster 1, cluster 2, sorry. Oh, forgot the other 2 data here, and then cluster 3. Why? Because you can easily see that this fits, this method of clustering fits the definition here. So data, in the same cluster, they're relatively closer to those in different clusters. So these are the things. Okay, so now after it, when we say closer, we need to define what do you mean by closer. So we define the opposite, which is dissimilarity. Instead of closer, we're actually defining further. So we have different norms, L2 norm, L1 norm, L0 norm, and coloration norms are here. And then indeed, it's easy to prove that this one and the Euclidean norm are the same. I believe I showed something here, so if you're interested here. And then there are also some mathematical optimization formulations to, formulate it to be a L0 norm of the clustering problem. Unfortunately, it's a NP hard problem. So, it's a beautiful mathematical model, but it's not applied. And then the next one, we introduced the concept of k-means clustering. The k-means clustering means I'm gonna assign the n data into k clusters such that the summation of the sum of dissimilarity measure of all the data into the centroid of their corresponding clusters is minimized. So I know this sentence may be very long. Mathematically, it may be easier, which is this. So here, the notation is Ci be the cluster of data I. So let's say, suppose I have 3 clusters and let's say 1,000 data. So C1 means data 1 belongs to which cluster. So my label is going to be 1, 2, 3. Or in Python, it shows starts from 0 always. That's going to be 0, 1, 2. Let's say XI, CI means data XI belongs to which cluster. So that's the thing. And because it's k-means clustering, where k is a hyperparameter. So totally we'll only have 1 to k clusters. Of course, again, I mean, Python will define it to be 0 to k minus 1. It's not a big deal. And then, excuse me. So mu L is the centroid of class L. So this mathematical form means that I only sum data I such that, the cluster of data I is L. So I will sum all the data in class L and divide by NL. NL means how many total how many data are in cluster L. So which means the mean or the average. Here we use the term centroid. Okay, so by the motivation or the definition k-means clustering, I want to do what? I want to minimize the summation of all dissimilarity measure for the data to their corresponding centroid, right? So I'm going to minimize this. Be careful that here my decision variables are mu's and the CIs. Here I wrote like CS because mu is actually a function of the CIs. A more explicit a model can be written like this way. The meaning here is that, okay, for each cluster L, I'm gonna calculate the distance of the data in class L from the I should say this, from the distance from data L to its corresponding centroid. And then I'm gonna do this and a summation for all the classes, all the clusters, not classes. Then I'm done. So, or we can write like this way, and then here V is this one, which means for L, for what for class L, what are the summation of the distances of all the points to its centroid. So here we go. Well, again, this problem is easy to be solved. It's easy to be modeled, but not easily to be solved. Again, NP hard problem, and hence we cannot solve. Explicitly in general, if even n as a medium size, so let's say 1,000, 10,000, those kind of size data will be very, very troublesome to solve it. And another thing is how to determine the hyperparameter k. We can use the Abel method. Okay, so here we propose the k-means algorithm to solve the k-means clustering problem. First of all, this is a heuristic problem. There's no guarantee that the decision gonna be the true optimum. However, it is actually pretty fast, and indeed we can use this method to solve large scale, like million-wise of the data, no problem at all. And it's worth mentioning that it's a special case of the EM algorithm. I'm not sure whether you are familiar with EM algorithm, but it's super famous in so many subjects, statistical related subjects. If you're interested, you can simply no, I don't think in my did I include it here? I don't think I included it here. Let me see. I probably didn't. No, I didn't. But if you're interested, you can just simply search it. Okay, then let's introduce what is the k-means algorithm. This is a very important. I hope you can code it manually instead of just everything by Python. Sorry, everything by the given library. Okay, so the initialization step is I'm gonna select k initial points. D-dimensional means because the data is D-dimensioned. So I'm gonna start these k points to be the initial k centroids. So it's gonna be this mu L. This one means it's in T1, or let's say iteration number 1. Or you can use 0, not a really big deal. And then when the stop criteria is not satisfied, for a stop criteria, see the next slides here, we're going to mention. Suppose we know the stop criteria, then I'm going to set t equal to t plus 1, and then update the centroid for all clusters. That means, okay, for the current iteration, I'm going to see for each cluster L, I'm going to say, okay, how many points are inside my cluster L? So I'm going to sum all these points and divide by the total number of the points in my cluster L, which is NL. So I will calculate all centroid. So here are some simple things. So when it's the first iteration, you can just skip it, go to step number 2. Otherwise, or if a cluster does not include any data, then we do not update a centroid, something. And then after step 1, I'm going to do step 2, which is cluster assignment. Then I'm going to assign each data to the cluster whose current centroid is the nearest. So I'm going to repeat these 2 steps, step 1, step 2, step 1, step 2, until the stop criteria is satisfied. When stop criteria is satisfied, so we're finished. And the return CI means, well, for each data, I'm going to have the return to the corresponding, the final cluster. That's it. Again, we just iterate these 2 steps, centroid update. So update all centroids for update centroids for all clusters, and then assign, which is okay based on the current centroid, which centroid should my each data I be. Be careful here, centroid is already updated. Okay, so it's not gonna be a dead loop. Okay, so then for some notations, you can just come here. These are the notations, and then the initial centroid actually plays a significant role. And then there are so many methods to choose a good, heuristically good initial centroids. And scikit library uses k-means ++ algorithm, which is one of the most famous one. And if you are interested, you can see here, there are too many things to mention. I don't have the time to mention it in detail. And the next thing, the stop criteria, here we mentioned. So there are actually many methods of the stop criteria. So for example, it can include the maximum number of iteration. That means at most I will run so many methods, so many iterations, or the maximum change in the updates. That means, well, among all the L centroids, I choose the maximum update of the centroid. The maximum update is in terms of 2norm, which means how far I update the centroid in terms of the, like how the location update. If the maximum of the update is less than or equal to a delta minimum, then I'm gonna stop. Or another method is the total change in the update, which means I'm gonna, instead of considering the maximum, I'm gonna consider the total of all clusters. So this is another method. Be careful that in the real application, you can combine all of them together. You don't have to only apply one of them, okay? So, okay, let's see some examples. First of all, I can, let me see, I should have something here. Let's save some time. I'm gonna directly run it. I'm not gonna Okay, so this is it too fast? Okay, so initial maybe it's too fast. Sorry about it. Yeah, I should have I should have applied GUI to make it a step by step instead of this. Let me see. Well, too fast. Let me give 1 second. Sorry about this. I believe I also generate this one. This one I just uploaded to to the Google Drive so that you can play this as well. So here we go. Where it is. Okay, iteration 3, 4, 5, 6. You see here, it's like iterating here. So 1 again. Maybe still too fast. Let me see. Is there a way I can just anyway? I'll try to recode it to make it stepwise. But here I guess it's easier. It shows step by step. So when you read it, it's gonna be in this direction. So it's gonna be like this way. This is step number 1, step number 2, iteration. Sorry, I should say iteration number 1, iteration number 2, and all the X. The first row means step 1, step 2. Okay, so iteration 1, step 1, iteration 1, step 2, iteration 2, step 1, iteration 2, step 2. Okay, now let's see step by step. So initially, as we mentioned, for example, we choose these 3 points as my initial centroid. Then step number 1 is what? Centroid update. So since we're in the first iteration, nothing to update because we have not assigned the clusters yet. It's my very first iteration, initial iteration. So I'm gonna directly go to step number 2, which is I'm gonna assign centroids. So how to assign centroids? So for each point, I actually don't know how many points I generated here. Probably several hundred. Let me see how many. Okay, so total about 4,500 points. So among these 4,500 points, for each point, I simply just write a for loop. I'm gonna say, hey, which centroid, excuse me, excuse me, which centroid is the closest to me? So clearly for all these points, this point, this one is the closest. Be careful that this one, for this one also, this is the closest. And then for all these points, this one is the closest. And you may have a question. Let me try to make it bigger. I can use control to make it full size. Okay, you may ask, hey, how about this one? Is this one empty? Yes, this one's empty. But it doesn't matter. As we mentioned here, if a cluster does not include any data, then we do not update. That's it. So here I'm not gonna update it. Okay, so I have these points, I have these red points. My blue point, so sorry, this is the green points are still here. And then my blue points are here. Step number 2, update centroids, which is based on my current clustered data. I'm gonna update the centroids. Okay, so here you can see for all my data, the mean is here. Again, simple, just count how many are there, and the summation all of these points divided by ML. Done. Super simple. My green data, because 0, so I mean 0 data is included in the green cluster. I call it centroid cluster number 2, let's say. So I'm not gonna update it. And then my blue cluster here, centroid number 3. Be careful here. The reason I make all these points to be black is because technically here I do not have any clustering information. Every time I'm going to assign a cluster in step number 2 instead of step number 1. And hence in step number 1, I make them to black on purpose. Okay, so now I have the new updated centroids like here. Then step number 2. Hey, for each data, which centroid should I belong to? In other words, I'm asking for each data, which current centroid is the closest to me. Okay, so here we go. So actually for half of, like these things, this one would be the closest. And of course, for all here, this one the closest. A small part of here, the green one is the closest. Then of course here, the blue one still the closest. Okay, down. Then step number 1, again, update centroids. Okay, so here are my green centroid, green points. So I'm gonna calculate the mean of them. Okay, so you can clearly see the mean gonna be somewhere here, which is here. Okay, for all my red things, and you can see the point of the red centroid is moved downward, right? It makes sense because I have more points here, many more points here than here. So of course I should move downward. So the red here, and then blue here, and green here. Okay, step number 2, again, assign centroids. So here you can see since, my centroid is already here. So what? So all these, the big block of the points, all of them now belong to cluster number 2. So these points, they no longer belong to cluster number 1. And then here, my clusters are number 1. Here, this one, the blue one's the most stable one. And then you just repeat again. And indeed, you can see, all these centroids are here, and also step-by-steps are here. Okay, now similar things here. Update centroids. Update centroids, sorry, and then here assign clusters, update centroids, assign clusters. And the interesting thing is you see these two. You see, they don't change anymore. So that means I'm gonna stop. Because once in one step they don't change anymore, you don't have to repeat, because if you repeat it won't be the same, it won't have any changes. Why? Because of this. The algorithms update super easy to understand. Well, if you have any questions, just let me know. So so like this way, we're gonna stop. So these are the things. And again, it's super simple. Basically just 2 steps. Centroid update, which is given based on the given centroid, I'm gonna update. Given on the current clusters, I'm gonna update the centroid, which means I'm gonna calculate for each centroid, for each cluster L, I'm gonna calculate the mean of the points in my cluster, and then I have all the centroids. Step number 2, based on the centroids, I'm gonna reassign the points to clusters. That's it. Okay. Let me see. Innovation I just provided. But I admit I made it too fast probably. Even myself cannot capture it. Okay, let me try to make a GUI while make it step by step, which is easier. But basically that's the thing. For for eye recognition, I believe oh sorry, what is that? I believe this one's the best. Okay. And also oh okay, here we go. There's another animation here. I feel mine is better, isn't it? Okay, so here are the clusters and then updates here. Okay, then the next thing is where are my uh no. The next thing is okay, Python. How to make this one in Python? Okay, let me see what is that? Okay, blobs. So I'm using the data blobs, and then I make the k-means clustering. This is the very first one. Let me code it. What happened? Oh, that's interesting. Let me just refresh this one, or maybe I can just do this. I realized I didn't turn off this computer since our last class. It's been how many days? 5 days. Maybe that's the reason. Maybe I need to reload the whole Anaconda. I'm not sure. Let me see here. Let me create a new one. Notebook. Okay, here we go. Now I'm gonna have lecture 11. What's the name setting here? Okay, k-means clustering. K-means clustering. Okay, so first of all, we are gonna what? We're gonna load the things, import numpy as import matplotlib.pyplot and plt. And then I can do what? I can do the k-means clustering from sklearn.clusters, I believe. Cluster import k-mean. Let me see. Okay, k-means, here we go. And then I will make the blobs, I believe data sets. Yes, sklearn.datasets from sklearn.datasets import make blobs. Okay, now I have all these. Sorry, let me move my computer a little bit. Okay, so now I have all these things. Then I'm gonna generate the data. Gener generate the data, and then I'm gonna say x y equal to make blobs, and then how many? 1003, and then number sample uh number sample equal to 1000, and then clusters equal to 3. Be careful that here people might say that hey, you're kind of like training cheating. Like how do you already know cluster equal to 3? 3. The reason we make x y like this way is it's just because of syntax. Yeah, I have to make it like this way. However, we want to use y so that even if I know kind of like I'm cheating, but I'm not gonna take advantage of this label. Okay, so and then I'm gonna train the model. Let's say train the three means clustering model. So how to train it model equal to k means. And then I'm gonna say the number of cluster equal to 3 and cluster equal to 3. Okay, now I'm gonna fix the model dot fix x. Again, I don't need a y. And then here I can use a y predict. Y predict means I predicted. I mean, again, technically it doesn't have any relationship with the y. Okay, now I can predict this one, and then I can, for example, I can let me see. First of all, let me see. I can print it. Huh? Oh my God, it's glitch. Cluster equal to 3, wrong? Okay. Not cluster centers. Okay, so let me see. Shit. Okay, so or I can print x dot shape at best. So it should be 1002. Yeah, because it's a 2D and I totally generated 1000 samples. And then I can also print y. Y should be, simply a vector between 0 and 2. Because we have three class. Sorry, y predict, but it will be the same actually. Yeah, actually between 0 and 2. Okay, now what I want to do is I want to get a centroids and then plot it, right? So the next step, what I need to do is to get let's say get us give me 1 second. Let me think about it here. So first of all, I can still get a centroid. Centroids equal to model dot cluster centers. And then so this one in this I will get a centroid and centroids, and you can print the shapes. Actually, I can directly print instead of shapes because total we just have three classes. So this is for class. In the following, let me follow the notation of Python. Let me call it class 0, 1, 2 instead of clusters 1, 2, 3. Clusters, the centroid of cluster 1, centroid of class 2, and then centroid of class 3. Okay, now I have all the clusters I need to plot, right? But the thing is, I need to know the labels because otherwise, how can I use different colors to plot it? So that I'm gonna say the labels of them are the cluster 1 is, okay, again, use this notation, I for I in range of shape, X shape means how many data I have. And then what I'm gonna do is if I, give me 1 second, if not I, Y predict I should be Y predict I equal to 0. And do the same thing for the other two things. 1, 2, 1, let me use this one, C0, C1, and C2. Okay, now I have these labels. I can do what? I can subplot. Subplot the original data first, and then I can subplot the data, let's say with predicted clusters. Okay, and the centroids, I will plot the centroids, I know it. Centroids. Okay, now for plotting the original data, it's extremely simple. Figure, create a figure, and then add an x. Let's say 1, 2, 1, and then I'm gonna add x dot plot. Here as just plot all the data. Use the black color and then label equal to let's say training data. X dot lab. Let's say that training data. It doesn't matter. Okay, here I don't need a plain central anymore. Here I'll do not show. Okay, so a set clusters equal to 3. What looks like this way? Oh, okay. So let me see. Actually, there are so many parameters here. The reason like this is because it's probably more, two clusters are actually merged here. Okay, and again, I mean, you can run different times. You will see many very different. Like here, it's clearly 3 clusters. Like just now must be 2 merged together. So this is the thing. Okay, now I have plotted the original data. I can plot the what? The predicted clusters, AX. Let me still add a thing first, add subplots. And now what I'm going to do is I'm going to plot the thing. Since I've already have C0 to C1, which will make my life much, much easier. X, let's say C0, 0. X C0. I really hate this keyboard. 1, but a very, very small keyboard. That makes typing so difficult. Label equal to, let's say, cluster 1, class 2, class 3, class 2. Let me call it class 0. Anyway, it's the troublesome for of this. B, and then it's going to be C1, and it's going to be C2. Oh, wait. Okay, here we go. So now I have all these things. I'm gonna do what? I'm gonna add a AX dot legend. And then we can have a look at it. Okay, here we go. And also, as we mentioned, we're gonna plot C point, the centroids as well. Then how to plot centroids? Simple, right? Because I've already had the centroid, so I can simply just plot the points. Let's say centroids are here. Let's say 0, centroids 1. And then I can let me see here what parameters did I use here? Oh, okay, KP markers as 12, marker edge color C. Okay. Why I need a marker edge color C? Okay, yeah, because it makes more clear. Okay, so I will have KP here. KP is something like, make a kind of this kind of shape and make it black in the middle so that it's going to be more clear. KP and the marker size equal to 12. And let me see, marker are so large. Let me just make this one. Marker edge color equal to C. I'm curious. Give me 1 second. I actually really forgot. Why do I need it? Let me see it. Let me use the KT here so that I can just matplot FQT. Oh, okay, here we go. So, okay, that's why. Otherwise, if you see, it's not that. So that if I give it an edge color, it will have, an edge here. So that, yeah, that makes sense. And, simply just to make it more beautiful. Okay, here we go. So you can see, I do have an edge color by comparison. See the plot I just made? You see what I mean? So here, there's no edge, but I mean, these are not big deals, to be honest. Okay, so here, this is how scikit-learn library automatically apply the what k-means clustering algorithm, to solve it. And see this image. Did it remind you something? Well, an interesting thing is my original training data, the raw data here, forgot to add to the title, but not a big deal. You can just add this. These small things, please excuse me. I'm not gonna follow everything, in my slides. And so here, my raw data are just all black data, meaning that I don't have the labels here. And here, I already actually somewhat gave them the labels. Why? Because well, I know for each data which cluster you belong to, right? For example, like this one is cluster 1, cluster 2, cluster 2, cluster 3. Don't you feel like this is actually very similar to classification in which I gave them the classes or labels? And indeed, this is one very important application of the actually the motivation, let me say, of the clustering, that such that after I have the clusters for the data, I can actually somewhat run the classification. So now the problem gonna kind of like be supervised learning and instead of unsupervised learning. And hence that's what we wrote here is based on the observed data set for a given metric M. For example, like in by default, in scikit-learn library, I believe in our life the same thing, which is Euclidean distance. So we train the model, and then we have the k-centroids, and then we can do the classification. But be very, very careful. This classification is a pseudo classification. It's not a real classification, okay? Because why this label cluster labels are recognized by us by the k-means clustering model rather than the given truth, like the labels given to you in supervised learning, like classification, is in general recognized as the given truth. However, in real applications, in too many things about when we handle data, clustering is always in the initial step, because but excuse me, by clustering for doing clustering first, I can actually have some general views and also eliminate many noises. Later we will see some examples. Okay, as another example, let me see what I'm doing here. Okay, what I'm doing here is simply to plot this one. So I believe, give me a second. Wait, what did I do here? Where's the P color? Why I feel that this code is wrong? Give me a second. Class selection looks like oh, here, it's here. That's why. So basically, what I did here was, so I have these two things as we did before, right? Okay, now what I can do is I can do this. Oh, I forgot this one, which is to actually set up the data. Let me do something here at legend so that I can, let's say, ax dot set idle the data, let's say with the data in clusters, and then I can say centroid. Let me see what did I do here with cluster centroid. Okay, /n. /n is just to change the line. I don't want to write everything all together. Centroids are centroids. Okay, here we go. So in this way, I will have okay. Then I need to set up the MP print options precision. How to spell precision? Okay. Precision shall be limited. Precision, yes. Precision equals to 2. Hope the life is gonna be easier. Yeah, now my life is easier. So the training data in cluster centroids is here. And now I can have what? I plot here, right? And then finally I can do what? I can make it a PMash grid. So I'm gonna have, let's say, a subplot the decision boundaries or decision, let's say, regions. And then I can have x equal to figure dot add subplot. Instead of 1, 2, I'm gonna have 1, 3 here. 1, 3, 1, 3, and then here 1, 3, 3. Okay, now I will have what? I need to have a mash grid, right? So I'm gonna have x1 equal to mp dot linear space. Linear space and then x0 dot main. What did I write here? 1 probably. -3. Okay. So again, this is just to leave some space because you don't want the points to be too close. It doesn't matter if you write 1, 2, 3, 4, 5, 10. That's really not a big deal. X0 dot max plus 3, and then 200. And I can generate a mash grid as with what we have done so many times in the class. Okay, now I have what I have all this mash grid generated. What I can do is I can define a color, right? So the I need to, if that case, I need to add more things from map plot lib dot color. colors every time I write, make it color and make it wrong. Import listed color map. Okay, here we go. And then I can have what? I can have dr predicted equals to model dot predict np dot array dot t, and then here use Ravel to make it to be flattened. X1 dot Ravel, x2 dot Ravel. Okay, now I can do what? I can define the color so that my colors, this is random color equal to listed map. And use our favorite color again. It's a light coral, light blue, light green. RGB, probably light green first. RGB and then light blue. Okay, now I can have x dot p color mesh. Oh, let me see here. Okay, so I need to use the color of my let me give me 1 second. Let me see here. No. Another thing, that's the next, that should be the next step. Then I can have the dr predicted where, be careful here when to reshape to the shape of x1 or x2. It really not matter. And then I can have the C map is simply equal to dr color. Okay, now I finished the this one, and then I need to plot the centroid, but I forgot the parameters. Let me see, what did I set up the parameters here? Again, the same thing. So I can simply just copy and paste actually. And then finally I can just print it. So here we go. It looks like I didn't write the title. And not big deal. You can just call it like decision boundary or decision region or whatever you call it. Not big deal. So here we go. And then you can see the decision boundaries here, and indeed it looks pretty similar. looks actually pretty similar, to here. So that's the thing. How we somewhat you take advantage of clustering to make somewhat like classification. Okay, so this is the thing. And then after it, we're going to introduce some applications of the k-means clustering. The very first and probably the most important application is image segmentation. So what is image segmentation? Which is for a given image, I want to partition the image to multiple regions or multiple segments with relatively homogeneous visual appearance. So those kind of segmentation, it is usually based on RGB of the color pixels. Of course, if you make it more complex, you can consider more levels. Let's say luminance instead of only RGB. You can consider many different like image levels. So here to make my life easier, because you will set up a lot of parameters, but here to make my life easier, I just do it on RGB again. So what's the point for me to do image segmentation? So the motivation somewhat is to simplify the image and emphasize the significant part. And another thing is I can actually save some storage space. Later we'll see why and how it can save the storage space. But here, let's say, suppose, we in the original image, here's just some theoretical things. Image contains n pixels. And then usually, because n pixels, n is usually very large, at least million-wise, could be even higher. Now, think about it. Nowadays, computers are all almost like 2000 by, I mean, the resolution is almost like 2000 by 1000, something like this. It's so easy to get a 1 million, 2 million, n millions, And so technically, all these n pixels, can, technically include the different colors. So at the most, I can include n colors. However, if by the k-means clustering, we can actually make these n pixels to include at most k colors, where k is less than n. And later you will see, for example, like those kind of examples, I make the whole picture to include only two. Oh, sorry. make these pictures to include only two colors. So think about the original how many dimensions you have. Here you only have two dimensions. So that could be a huge like dimension reduction. And then here someone actually proposed. Here I just cited it. So wait, why is it download? Don't tell me my what is wrong. Oh, okay. Here I don't know why it's in this way, but basically you can just download here. I believe I set up the share to be everyone, right? Did I? Yeah, anyone with a viewer can view. So I believe you can download as well. So anyway, I don't know. So let me directly open my local document here. So someone proposed a propose an estimation ratio, and actually this is a very compared with n, this is indeed a very small number. Like think about it, 3m times 8 versus this one, and this is actually, if it works, it actually could be a very good ratio of image compression. And then this kind of this image segmentation is widely used in things like image enhancing, image compression, or even radiology. We'll see MRI scan here. Okay, then let's see how can we play this game in the MRI scan. So remember, we got this actually in what? In an example, which is, let me see whether I can. Let me see whether I can just copy and paste from. No, I'd better not to do it. Okay, because if I copy and paste from the example, I'm talking about this example. From this example, it could be even more troublesome. There is a campus recognition. If I copy and paste from this example, it could be much more troublesome because I need to recode everything. Here, the good thing is that I don't need to recode. I can just simply write it. Okay, so where's my what? My Jupyter notebook. Let me add a lot of things here, and then let me see how can we do it. So first of all, I just copy and paste everything here. I don't need this. Actually, I don't need these three. I just realized one thing that here, and okay, and then I'm gonna do what? Let me see. I define a class here, right? Actually, I don't have to define a class. They're not a big deal. Okay, I define a function, not a class. Okay, so I define a function. Define, let's say K means picture. And then the only things I need is first the path of the picture, and also I need a K list. Let me see, is the K list here? Yeah, I do need a K list to what? I need a K list to include what case do I need, because here I believe I tested 2, 3, 5, 10. Okay, so let me do this, otherwise I'll forget for sure. So that I can have what? I can have the path, no, not define. Path equal to, where's my MR scan? And here, sorry, here I do not write it to be two rows because I've written, so it will show you an error. So here I'm gonna have K list equal to forgot again, 2, 3, 5, 10 maybe. Yeah, 2, 3, 5, 10. 2, 3, 5, 10. Okay, now let's see how can we do this one. First of all, I need to load the map. I need to load my map, the image, so that I will have, let's say, let me see here. Sorry about it, forgot. Oh, okay, here. I somewhat make the problem actually more complex because here I believe I'll read the length of K list. Okay, gotcha. Okay, so first of all, I will make the length equal to the length of k list plus ones because again, Python start from 0 instead of 1. And then I'm gonna have what I'm gonna have let's say I need to define the row and the columns first. So first of all, because suppose my k length is L. So what I'm gonna do is kind of like have a square root of L and have the ceiling function to make it, integer to be plus. So that since my scoring is, like a rectangle in which the length is actually longer. So I'm gonna do, the column first. So I have the subcolumn equals to mp.ceil. I need to use a ceil function. And then here I'm gonna have square root sqrt of L. And here I believe I will need to ask let me see, but probably I will need to ask as type because this will not give me let me do an example. Well, that's the reason why I love Jupyter Notebook. I can say for example n equal to L equal to 10, and then let me do it like this way. Okay, here we go. That's the reason why you will need dot as type integer. This is because later we will use this information to be the row and the column index. And the row and the column index only accepts only accepts integers instead of floats. This, although the number itself is 4.0, but it will be considered as, a what? A float. So for example, if you just ignore this one and then type subcode, you see number float. But if I write this way, integer, here we go. So that's the reason why I do need to have dot as type integer so that I here can define the column and then sub row is going to be relatively simple, right? Since I already have the column, I just need the what the total number of the length divided by it. So that's still again, to make my life easier. MP dot wait have the L divided by subcode directly should be the answer. Yes, and then I need to have as type IT as well. Okay, so now we can just play something for fun. L equal to, let's say, 10. Oh, okay, so great. So if L equal to 10, it will give me a 4 by 3. 3 by 4, sorry. Row first. 3 rows, 4 columns, which is absolutely correct. And then suppose L equal to 12, it should be the same. 4 by 3. But if it's 11, it's going to be 4 by 4. So sorry, 13, it's going to be 4 by 4. Okay, so here I've already figured out, how many rows and columns that I'm gonna have. Now I can just read the image equal to PL sorry, no, not PLT. Let me. Yeah, it's correct. No, because I was thinking about PLT dot plot dot image read. Yes, image read. And then what I'm gonna have is image read path, and then I'm gonna create the plot. And then subplot subrow first, subcolumn is here, and then let me see, and then I will have. Okay, here we go. Now let me just give it a title. Original image. Okay, I just can just first run it. Okay, here we go. I do not set up the axis off on purpose because you can see the scales. Or if you want to make your life, looks more beautiful, you can just simply dot axis off so that you will not see this X and Y ticks. You can see it's all empty, but here, let me just, let me just keep it because, it's gonna make, see the comparison, the size more clearly. Okay, now I've already loaded the original image. What I'm gonna do is that I can actually write a note here. Load the image. So now I'm gonna train the k-means clustering algorithm. K-means clustering training and the subplot. Okay, now I can do what? I can do let's say my sub number equals to 2. And then I'm gonna for k in k list. So for k in k list, what shall we do? We first need to train the model, right? So we'll have model equal to k-means. And then here I have n cluster equal to k. Okay, now I can just fit model dot fit image. Wait, let me see. Give me 1 second. Give me 1 second. Wait. I need to do something here. Sorry about it. I need to have the give me 1 second. A few minutes. Let me print. This is something wrong. Print image dot shape. What? I done close it automatically. Image dot shape. How come 4x4? What? Oh no, 4x4 is the next one. No. Wait. Here now. Let me just. Okay. Here we go. Well, it is not what we want, because let me first delete this one. So this is a tensor. So it has row, column, and then I don't know what is that one called. So what I need to do is I need the data to include only RGB, and hence I need to make it to be like this way. 255 times 201 equal to this number 51,255. I needed to include the 3 columns and these rows. So what I need to do, I need to reshape it. Otherwise, I cannot fit like this way. For sure, it will be error. If I fit this way, it must be the RGB. So that what I'm gonna have is I'm gonna create an array that's called image array. Equal to reshape image dot reshape as we did before. And then you can definitely put this number here, 51,255 and 3. Or you can just make a -1. The -1 here means I'm gonna say, hey, Python, you calculate by yourself. It's your job to calculate, right? How many rows, but the columns I make it to be 3. So if you're writing this way, let's say I print the shape, I will print image array dot shape. You will have this. So this one. Wait, hold on a second. Okay, here. Line 33. I'm trying to k-means class. Oh my goodness, when did I delete this one? Okay. And then you're gonna see this number. See it? 51,255. So Python will calculate it by yourself. This is a very magic point of -1. You don't have to calculate it by yourself. So that's the thing. Python can calculate it for you. Okay, now let's do the k-means clustering. So here for the fitting things, I'm gonna fit based on this array. Okay, it's no longer a tensor anymore. Okay, so now I have what? I've trained the model. I've fit the model. The next one I need to do is I need to plot it out, right? So I'm gonna say X, I, and J's for I in range of image dot shape 0, for J in range of image dot shape 1. What I want to do now here is I'm gonna get the what? Get the give me a second. Give me a second. I'm gonna calculate the what? I'm gonna calculate. Uh, I'm gonna get a label. No, I should use the term cluster instead of labels. So here is for IJ's image here. I will load the RGB data, and then after getting the RGB data, I can predict which cluster it belongs to. So yeah, no matter what you will do, it doesn't matter of the order. I don't know the order, whether it's the same as in my slides, but no, not no matter what, I want to do it. Model dot predict image. Let me see. Here my image gonna IJ, and here's the thing. Of course, for the IJ, you can based on the shapes of image, you can calculate it based for the index number of an image array. You can do it as well. But here I just want to save my life, so I directly use image IJ in a column. You know what I mean? You can just simply transfer between the two, numbers, index transfer. So here I'm gonna have this one again. I will reshape it to be -1, 3. So here I'm gonna cluster predict it. And remember what we did here? I remember this because I always made a mistakes here. When you do this one here, it will give you as a 2D array. And so we're gonna write it this way, because if we don't write it in this way, suppose it's gonna be, let's say, cluster 0, it will give you cluster 0 like this way. But what I need is 0. Why? Because I will use this one to do some index operation, and hence I need to add this one 0. So this will give me indeed a number. Okay, now I have calculated the clusters. What can I do? Is I can directly let me see. Give me 1 second. Give me 1 second. Let me think about it. If that's the case, what I can do is, okay, I can replot the image here, but how to replot the image? I can simply use the centroid if I have already calculated the centroid. And then I can, let me see, here is, okay, gotcha. So I need to do something here, looks like. Where's the place I train my, oh, here we go. So I have here, I need to calculate my centroid first. Centroid equal to model dot cluster centers. And then one thing is that because we're doing RGB here, so that it must be integers. Let me use this. Round to integer, and again use as type. Otherwise, it may be wrong again. So now here I have calculated model, I have calculated centroids. So what I have here is I have the cluster prediction, and then I can do what? I can just okay, then if that case, then I need to regenerate another matrix here. I can call it, let's say, image dot clustered and e.array. Actually, no need. I just directly use np.zeros, which makes my life easier. And then I just need image dot shape. And then to make my life easier, I can make everything to be integer. Again, why? Because it's RGB. That's why. And then I can now I have this one. Yes, now I can recode it. Now my life becomes much easier. Clustered, simply let's say IJ. This equals to what? The centroid of the cluster. Centroid of the corresponding cluster. Okay, and that's also the reason why you need this, because if you don't have this one, this number won't be a number. This will be an array, and then we'll make it wrong. Okay. Then here, after this, I believe I've already replaced the things here. Then I can what? I can actually print it. No, not print it. I can plot it. Figure out add subplots. Then I can have sub of the row, sub of the column. And then I have the sub number. Always remember sub number plus plus. If it's wrong, everything gonna be wrong. I know I will. I may forget it, so that's how I write it now. And then I can add a subplot, and now I can really plot it image show, which is the image clustered. Image clustered. And then I can do ax dot set title. To be what? To be, let's say, the image reconstructed, let's say by k means love story. Why don't I write this? K means love story. Okay. So now let me see here. Okay, K means color story. Then let me see here. Do I need to do anything else? Yes. I need to have a PLT. Oh, interesting. Is that running? I'm not sure why it takes so. Oh yes, yes, I remember it. When I was making the what it's also very long. Let's wait a little bit. As you can see here and also here, it shows that it's running now. Okay. Or maybe I can make it small. Let me stop it. Okay, or maybe I can just make it a two because I just want to make sure that I don't have any mistakes here. Sorry, I do make it again. Oh, already done. Good. Oh, wait, something wrong. Come on a second. That shows. Let me see. The time should not be. I know the time won't be short, but it should not be that long. Let me just turn off everything. Okay, so to make sure that I know what it is doing, let me print the K here. Okay, K equal to 2. And then when is K equal to 3? Oh, well, I probably should have the, I'm not sure. No, this will create something. Let me see here. Did I make some mistakes here? What is that? No. Let me go back to my slides here. Interesting. How come so slow? Uh, Okay. Original images here. Give me 1 second. This number equal to 2. Yeah, I already did this. Hmm? Okay, while it's running, we can actually have directly have a look at the results to save us some time. So here this is the original image is here, and this is the two means clustering, and I believe you've already seen that the point is here. So for a normal person, the head there should be no something like this here. So this is clearly a tumor. What I want to do is I want to use the k-means clustering to cluster the image from an MRI scan or MR scan here, and then I want to show something significant. So this is also the meaning when you go to the very beginning here. Let me see where it is. Let me see. Okay, so here clustering image, we clustering definition, which is we want to make the things that are close to each other to be one group, one cluster, and others in other clusters. And then here we mentioned the motivation here, which is which is we can emphasize the significant part. And here, what does significant part mean? Clearly, this is a significant part. So this is the thing. And then I give it only 2 clusters. So you can see here cluster actually means colors because I only do the clustering based on RGB. So here there are only 2 colors. And well, if you're familiar with, if you're good in coding, have a question, think about it, how to write a code to automatically detect the size of here. You may need to run some interesting, kind of like the interesting algorithms, which is, for example, you start from here, you show a radius here, so that you should always, if you detect, let's say, a line, let me plot a line here. So I plot a line here. You should always, get 2 of them, 2 of the, oh no, it doesn't make, yeah, because here looks like there's a small point here. Let me think how to, or I can start from maybe here. Let me see. I'm not sure, but there should be no there should be not too difficult like algorithm to detect the boundary and hence calculate the size. Well, the easiest way you Monte Carlo, Monte Carlo. So this method, this is one method. But indeed, based on here, you can actually get to the colors and then hence you can calculate, the size of here. And similar, this is after 3 means clustering, it's gonna be something like that. Till now, how could this be possible? Uh, that's interesting. Yeah, only this one is running. I don't know why it's so slow. Till now, it should be already be completely done. Well, anyway, but the result is this one. And then here the 3 means clustering means that I have three colors. And indeed you can see pure black color, this is relatively white color, and this is gray color. So 3 colors, 5 colors, 10 colors. Of course, with more and more and more clusters, your image is gonna be closer and closer to the original image. But this may not be my purpose. My purpose is to emphasize the significant part, right? Here we go. This is a significant part. Okay, so this is one thing. Another thing, another thing that's just for fun. Here's a ragdoll cat, and then well, the cat is pretty cute. And then, I want to somewhat like show the shape of the color of the cat, so I can do k-means clustering as well. But be very very careful. One thing here is that our background is white color versus the cat here, the cats here happens to be white color as well. And hence, in this specific example, k-means clustering, two-means clustering may not be a good idea. And many of you have seen those kind of like movies, especially put those kind of CGs in movie. The background is always use a special green color. Why? Because that special green color is not very common in the natural color system. It's not the green like the trees, grass, those kind of green. It uses a very special code of the green color, sometimes blue color. And hence, I can easily, no matter I use k-means clustering or segmentation methods, I can easily do the segmentation and get the shape, the contour of my what the interested part. And hence, I can filter the background. Imagine that suppose the background of this one is all green. I can easily use image segmentation, dig this cat out, you know what I mean? And then I can replace the background. Let's say I put it in the universe, and you're gonna see a cat smiling, sitting and smiling to you, in the universe. So that is some applications. Okay. I must have something wrong here. Otherwise, how could this be possible? Till now not running. Let me see. Let me stop it here. I'm not sure, however, that's pretty interesting, huh? Because this one works, right? Does it work? This one also doesn't work. See? Yeah, this one works very fast. Now how come this one doesn't work? It doesn't make sense. Well, I for J here. Oh, that's interesting. I'm just curious. Let me see here. Let me see here, print K, and then it just kind of like stops here, and then let me see. Clustering equal to this one, and then let me see, did I make any mistakes here? Oh, wait. Here's I did have defined. Well, I guess I know the. Okay. I guess I don't know the reason. No. Let me see. This is in the K. Yes, in the K. No, this is still correct. That's interesting. I'm not sure where it is something k-means clustering. It is in the K, and then here for the IJ cluster equal to this one. But why it doesn't show me the error information? Because if it's the R, it should show me immediately the error information, right? Because I never defined a sub R. Okay, let's do it again. That's interesting. Anyway, I will try to check it, after the class. And if we have something, yeah, I hope I can fix it. Although it's really not a big deal, we just feel not comfortable. How come it looks like everything's correct? It didn't show any error information, but finally, shows the result is wrong. That's I I don't know. Honestly, I feel it could be something about the Python core here. But anyway, since our time is here, I'm not gonna waste the time here. So I will try to fix it after the class. Okay, let's go to the next topic, which is the last topic, PCA, principal component analysis. So here I can terminate it. Okay, this one. So here the main reason for PCA, principal component analysis, is for data dimension reduction. Just now in k-means clustering, we've already seen a technique, for data dimension reduction. And here's another thing. The good point of PCA is that somewhat it can capture more information. So first of all, let's have a look, at data reduction in general. So in general, it is something here I have D feature, the original data, I have D features, And then data reduction means a feature reduction. Okay, data reduction don't mean, let's say I give you 1,000 training data and then you make it to be 10 training data. No, it's the feature reduction. Suppose originally I have D features, and D could be a very large number. So for example, like consider our images. Remember, we always vectorize the image. In other words, the dimension would, in terms of the vector, the dimension would directly be the size of an image, which could be pretty large. Again, let's consider 2,000 by 1,000, which is 2 million, the dimension. And then the data reduction or dimension reduction is actually to transfer a data set from a high dimensional space to a low dimensional space, such that in the low dimensional space, the significant part are still there, are still kept. Specifically, if the low dimensional space is 2D or 3D or even 1D, then we can easily visualize the data. But the problem here, again, I use the term significant information. What does it really mean on the significant information? Because in mathematics, everything should be defined very clearly. And then, so we can actually, have created one definition. So, first of all, significant information this is a very wide, a very general concept. I mean, it really depends on different data sets or problems. But in general, we can define, like, if a data in a data set differs a lot in one direction, then this direction is somewhat significant or representative to the data set. Because it's somewhat like shows the feature, shows the difference in this direction. I know this may not be that easy to understand. Let's see an example. I believe everybody knows this guy, Steve Jobs, great person. So first of all, let's have a look at this picture. So this picture is 750 by 1296 pixel. I mean, the original picture is actually pretty clear. I just, to make it to be into my slides, I just, make it to be very small. And then, which is 97 2000 pixels. The second picture is 323. The third picture is 470K pixels. First of all, if I ask you this picture, who's this guy? Who's this guy? Steve Jobs. Everybody knows it. Number two, who's this guy? Steve Jobs. And you see, the point of a person, to show a person, the most important thing is what? Is the face, right? By comparison, if I give you the third picture, who's this guy? Who knows? It can be you, can be me, can be anybody. Even if I ask you for the gender, this may not be that easy to say. You cannot say because I wear the suit or because my hand looks like this way, so it's male. I mean, it can be a female as well. It's very difficult to see. So what we see here is that suppose there's another person. Let's say, suppose I stand there, and then I wear the same clothes, and I put my hand like this way as well. So what's the key difference? How can you differentiate me and Steve Jobs? Simple, the face, right? So you see what? In other words, in terms of face, this part, me and Steve Jobs differs the most, right? So this is the meaning. That means it's this area, the face part, is a significant information. And again, you can see why this definition works, because in terms of face, two people differ the most. So this is, in other words, this is the thing for each person. It's the most representative part. You see what I mean? So that's the reason why, let's say you go to those kind of offices, let's say it's gonna have a list of staff members there, and then with the name A, B, C, D, E. Everybody is gonna just put the face there. So why don't you put a hand there? Because by the hand, I cannot recognize who that is. Face is the most significant part there. Or let's say in terms of face, people differ the most different. And this is a principal information or the principal component. In this specific case, I cannot directly claim it same principal component, but there's no doubt that it's the most important, one of the most important part. Of course, specifically for Steve Jobs, that's another thing. Apple. Say I just give you a picture like this way. I cut a face. I just show a person, holding an apple. you will probably guess that's Steve Jobs. So for Steve Jobs, Apple is, another extremely significant direction. So, but in general, this conclusion doesn't work. I mean, in general, we're gonna show people's face. And that's why we can, naturally define the most significant information by the direction or the area that, the data differs the most. Okay, another examples here. So you can see this is the original 2D data. And then this is based on my two original features. So original feature 1 is here, original feature 2 is here. But you know what? We don't have to observe this data based on this coordinate. We can observe the data based on this coordinate, which is V1, V2. You see, what's the difference? The difference that clearly the data, the divergence, or let's say the difference of this group of data in terms of V1 is way, 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 way bigger than the difference in terms of V2. Why? Because V2, you can see, V2's difference is just such a small part. Let me just give me a second. Let me plot it here. Let me use, let's say, the yellow color. So in terms of V2, it's even too small to plot an arrow, but it's just a distance, very, very small distance. But in terms of V1, see, my distance is so big. And hence, V1 is actually my main difference. And since the difference is so big, I may even consider to ignore dimension V2 so that I will project the whole data on only one axis, which is V1. And this is possible. And this is also the meaning of, later we'll see, PCA is exactly that thing, that I will project everything to be V1. And then I'll reduce the data, the dimension from 2D data to 1D data. And the third, wait a minute. Here's kind of like a data rotation things. And if you are good in linear algebra, you're gonna see this is nothing, just a original data times the rotation matrix. That's it. But here, assume that I don't know what is the rotation matrix in 2D or 3D. Then I'll try to brutally explain it. So let's consider a data X. This X, let me make it bigger. So this X, on the original feature space I1 and I2, my coordinates are x1 and x2. So I can write x vector equal to x1, x2, which, x1 is the coordinate in direction I1, x2 is the coordinate on direction I2. Okay, now strictly I should write it in this way, right? So let me underline it. Strictly, I should have x equal to x1, I1 plus x2, I2. Okay, simply because it's a vector. Now let's consider an orthonormal, new orthonormal basis, which is V1 and V2. Why this one is always here? Let me see, because I already. Okay, let me see. Here, let's consider this one. Orthonormal means, I don't know why this one. Did I show always in the front? I don't believe I show always in the front. I don't know why, even if in the full screen, my text bar is still shown here. But anyway, so orthonormal simply means, first of all, the length of these are unit. In other words, the norm equals to 1. And another thing is that they are, perpendicular. In other words, the inner product of them is 0. Okay, now I want to know what is the coordinate of x on V1 and V2. In other words, what are these two numbers? And then we can simply do the projection. The inner product of x and V1, inner product of x and V2. These two are the coordinates. Why? Because the inner product is what? As cosine. Remember it in high school. Inner product, we can use a formula. Inner product is somewhat like the cosine. So if you have the x side this way, isn't it here? And isn't it this one here? So that's the reason why I can simply use inner product. Okay, now by this way, for any given orthonormal basis, I can project my x onto this, the two bases, and then get the corresponding coordinate here. Okay, what's the point? See the next one, you will know it. Okay, so first of all, that's here to save my life, I'd already coded here. Okay, let's run it and let me open the project. Okay, here we go. So let me just run it. Okay, so I will have a 3D plot. Okay, here we go. And then you can see this group of data, the most significant thing is what? So first of all, the original direction is feature 1 here, feature 2 here, feature 3 here, right? Original thing. But you can see, let me use, let's say yellow color, let's say blue color. Okay, this direction, let me make it bigger, okay. In terms of this direction, it has a big change. And then in terms of this direction, the change is small. In terms of this direction, the change is even smaller. And hence, you know what? This direction, it dominates the change, the difference, isn't it? And then later we'll see how can we, like for distribution X, how can we describe the difference? One super simple thing is the variance. Given for a given distribution, the bigger variance is, the bigger difference it is. Okay, so here we go. So now immediately I'm gonna think, so why do I really need a 3D to express this data set? Maybe since the difference in these two directions are so small, maybe I can just use one direction here to represent the whole data. Yeah, maybe. Okay, so these are the basic concepts of dimension reduction. Now let's see, how can we really make it? So the idea, as we just mentioned, for PCA, principal component analysis, is to consider directions at which the data set differ a lot as significant directions. And then we're going to make an analysis towards the new directions, and hence it's principal component analysis. And these significant directions are called the principal components, PC. Okay, but again, what does difference really mean? We can, like I just mentioned, we can use variance, right? But here we can list 3 questions. First of all, find the mathematical expression of variance for the original on the original feature basis. This variance should be what? Based on the distribution of X, based on your given training data, on the coordinate of your original features, okay? Then we will try to project the data onto the new features, which are the PC basis, and then find the expression of the new variance. The third step is I need to find the expression of the most significant, second most significant, and blah blah till the least most significant directions. Why? Because I want to do the reduction. As long as I have, an order, like a sort of all of them, I can simply, based on some criteria, I can choose how many PCs, principal components, are needed, right? Because if you use a D, originally it's a D-dimensional space, and then you just project again on the D PC. So what's the point? It's just like you look at a different angle to see the data. Nothing's reduced. But actually, many things can be reduced in homework. No, there's no homework. Maybe in exams, you will see a super interesting example by the figure Mona Lisa's smile again. Because I said again because in homework too, you should have seen the Mona Lisa with a mouth cover already. Something just for fun. And then you will see how crazily, the dimensional reduction we can apply there. Anyway, let's go back to some theoretical parts here. And here are some notations for random variable at y. The reason here I use y instead of x because I need to save x for future use. So I use variable y. So variable y, which is d-dimensional, its variance can be calculated in this way. Again, be careful when I write the capital letter, that means it's a random variable. So Vy is defined by this way. If you want to know more, then well, it will be pretty, I mean, we need some time. But if you just consider y is 1D, one-dimensional, then this is super, super simple. This is exactly nothing but a difference of the variance. And then here, the covariance matrix, the ijth element is a covariance of feature I and feature j. So we go back to our problem. So first of all, remember we mentioned the full dimension, the original dimension, the original space has d dimensions. So for each data, I can write it in this way. Let's say data one is x11 to x1d. Data n is xn1 to xnd. So now let y denote such a random generated data from our interested data sets. And then this means these x1 to xn are all xn realizations. So based on the observed data, first of all, I can calculate the mean of the mean of this y population, which is summation of all the training data divided by n. Be very, very, very careful that this mean is d-dimensional, not n-dimension. Be careful, okay? Because later, you will see later, when we discuss more calculations, it's super simple to get it wrong, and people may think this n-dimensional, then everything is wrong. Okay, since we have EY and we just plug in this formula inside, you can immediately get this one. So here's the variance expression of my random variable y. And then we are gonna shift it to the center. So which is for each data, I'm gonna, move it like this way. Be very careful here is, let me get something here. So here, my each data is defined in row. The reason I'm writing this way because Python did the same thing. So that here, I made it to be row. It's not like column vectors anymore. Each data is kind of like a row vector. It's like this way. It's kind of like, okay, I wrote it here. It's x1 minus x bar t. Okay, again, x bar means the mean in each feature. The mean in each feature, not the mean of all training data, but the mean in each feature. Okay, so for each xi, I minus the mean in each feature and make it a transpose, because here my x definition is still the column vector. Okay, so here we go, and this matrix should, the dimension should be n by d, means I have total n data, and each data has d dimensions, so n by d. And z is the shifted mean. The reason is because think about it. Let me make it. Let me see here. Okay, so for suppose I have a lot of data. Let's say let me just create several points. Let me create some red points here. So suppose why this color? Okay, suppose I have all this kind of data here. What I want to do is that I always try to move to a coordinate such that the mean is centered in my origin. So first of all, I can definitely use this specific V1 and V2. But the bad point is that you can see all the data are in this direction. So instead of using the current V1 and V2, why don't I use this one? Let me use let's say, let me use a blue color here. Why don't I make this one? So in this case, I can make like the center, the mean of the data group to be, to my origin. This will make my calculations easier later. So this is the reason why I need to define the z. Basically, I move the coordinate to be the center. I move my origin to be my mean. Okay, now use this definition. Since this one is z, this one is z. Actually, this one is zt. Sorry about. Here are the column vector. Here are the row vectors. So that I can directly write y v1 variance of y equal to 1 over n ztz. Okay, now we discussed this on the okay. So now for a given vector v and the raw vector, we want to project it onto v. And as we just mentioned here, super simple. The coordinate, let's say, what is the coordinate of my current v1, v2 system? So here is just a projection of x onto v1, projection of x onto v2, right? Okay, so similar things here. I just make a projection here. So this actually solved the second question. Okay, now what we can do is that I want to project all the raw data, so many, all of them onto V. then what can we do? We can actually take advantage of this one, and we can rotate this way because of why this gonna be give me one second. Let me see here. We take advantage of it. Okay, now I give you a unit vector v. Then I'm gonna ask you, hey, how can I calculate the variance of this? So what can we do as VTV? Because what? Because here, this one is based on what? This one is based on my original data feature, which is the D spaces, the D-dimensional spaces, and this one is I give a whatever a vector v. What is the variance on this v? And I can use this formula. This is actually relatively easy to be understood. Why? Because you can okay. I guess I'd rather directly use my hand to write it easier. So you can directly consider it before we have the z, right? You can directly consider like this way. So remember, here we have z. You just replace this zt to be zvt. In other words, you replace the z to be zv and then also zv. So this equal to what? This equal to vt, zt, z, and v. N over 1 is just because the variance. That's why I mean n over 1 is a constant. You can just ignore it. So this is the expression. That's what we have here. In other words, I just project z onto v, and then here I do the variance. So this is the thing. Let's see an example. So let's consider two data x1. Where's my x1? Sorry, my x1 is here. These two are the projected number. Okay, so x1 is here, which is 0, 2. X2 is here, which is a 4, 0. And then we can easily calculate the x bar. So x bar is for the first element is 0 and 4. So the mean is 2. For the second element is 2 and 0, 2 and 0. So the mean is 1. Simple. So that my z is what? Z is just each x minus x bar. Be careful when I say z, x would be written in a row, which means 0, 2 minus 2, 1. So it's negative 2, 1, and for x2 the same thing. And hence, by this equation, we can calculate the variance under the origin basis, which is this. And I believe this is super easy to be verified. For example, we just consider, let's say, ignore the covariance. Let's just have a look at the variance in first feature. So we have 0 and 4. So 0 and 4, the mean is 2, right? So how to calculate the variance? Remember, 0 minus 2 squared plus 4 minus 2 squared divided by 2, because I have 2 data. So it's going to be 4 plus 4 divided by 2, which is 4. So you can verify the second number is the same. So this is a covariance matrix under the original basis. Okay, now let's consider I'm not interested in the original basis. I'm interested to project the variance onto a specific vector, which is this square root of 2, which is just 45 degrees. And the reason I make it a square root of 2 over 2 is because I want to make it to be a unit vector, meaning that the length of this is 1. That's why. Okay, so now I can get the corresponding coordinate for it. So for x1, my original one is what? 0, 2, right? In order to get a coordinate projected onto this direction, I'm gonna have 0, 1 in the product of square root of 2 over 2 and the square root of 2 over 2. And I get square root of 2. In other words, this length, you can see it. This length is square root of 2. And similarly, for x2, my original, the data in the original space is 4, 0. I can project this one onto it. So this one number times 4 plus 0. So it's going to be what? It's going to be 2 times 2 square root of 2. So these are the same. In other words, these two, in this v, my coordinates of x1 and x2 are square root of 2 and 2 square root of 2, respectively. So now I'm going to ask you, hey, how to calculate the variance, of x1 and x2 on this direction? So now I have square root of 2 and 2 square root of 2. Then how to calculate the variance? Essentially, we calculate in this way. This is the, the very fundamental definition of the variance, right? First of all, I get a mean. So square root of 2 and a 2 square root of 2, the mean is 1.5 square root of 2. And then each data minus the mean square plus another data minus the mean square, and then everything divided by 2 because I have two numbers. So according to the original definition, I should have the variance equal to 0.5. Now let's verify. I can use this formula to directly get the variance equal to 0.5. So here, V is what? V in our original space is square root of 2 square root of 2. And then 1 over n equal to 2. And n means how many observed data. I have two observed data here. And then my Z matrix, where? Here. Here's my Z matrix. So ZT is a transpose, and then Z is here. And I just do this. I mean, I'm lazy to open the MATLAB to calculate it. But I mean, yeah, or you can just actually this calculation is super simple. You can easily verify it. The result is also 0.5. And hence, we can use this method. We don't have to like project again, make different steps again. This method is gonna be way easier. Okay, now I have this. I can more formally define the problem of PCA. Again, the idea is what? The idea is I want to find the direction at which the data set differs the most. Okay, so, and differs means the variance. In other words, I want to find the direction project onto which the data set has the largest variance. So in other words, suppose I give you this one, I try to find out this V1 at which direction the difference, the variance of this training data set gonna be the largest. Okay, now we can define it in this way. As we know that for a given V, the variance projected onto V is this one. I want to maximize the whole thing. And here I can ignore 1 over n, which is just a constant. So I'm gonna say maximize VT, ZT, Z, V, subject to the norm of V equal to 1. Why the norm of V equal to 1? Simply because it's a unit vector. That's our definition. Otherwise, you want to put a weight parameter W here, which makes my life more difficult. So that's the thing. And then it's worth mentioning that this problem is a special case of the Rayleigh quotation problem, which should have a denominator here as well. If you consider, yeah, which a denominator here, but because my V is a unit vector, so this is always a 1. So I can save my life. That's the reason why I want to define this one. Okay, and here's a little mathematical part, which is about KKT conditions. If you are interested, you can just see more information here or see my slide, not slide, what's called extensive reading here, which shows you like a more general explanation and the motivations why I need to make these things like this way. If you're not interested, then you could just pass it, not a big deal. So that in general, the KKT conditions is just a necessary condition for local optimality of nonlinear optimization. But here, my V, be careful, V is my decision variables. So this is a quadratic form because ZTZ is, a just semi-definite matrix, positive semi-definite matrix, so that I can write it, not write it, so that this KKT condition, the local optimality gonna directly be the global optimality because it's convex. So you're gonna have only one. And these are the details of the 4 conditions here. But here, since we only have one equality condition, we don't have those inequality conditions. So we will finally only have 2 constraints, which are the stationarity constraints and the complementary slackness conditions. And then you just plug in, these 2 things here. You just substitute a number here. So this nabla is a gradient operator in terms of V. This equal to 0, and we can get what? We can get this, because this is just nothing quadratic. It's just like x squared derivative is 2x, right? Similar thing. So ZTZ is like a constant. You can just keep it. And then we have VTV, but the gradient, the nabla operator is based on V, and hence I just take a V out. And here's even easier because, I have a 2 and I put a V here again. And then, so we get this equation. And finally, we have what? In order to solve V, I must satisfy this equation. And the second thing, we just keep the same thing, primal feasibility, which is the V is a norm vector, unit vector. But if I give you this one, does it remind you something? isn't it the form of eigenvalue and eigenvectors for matrix ZTZ, isn't it? So this is from here, I immediately find what? I immediately find that V should be what? My eigenvector. And this lambda is actually my corresponding eigenvalue. And because ZTZ, the dimension, is D, so it must, in general, okay, in general, it should have D eigenvectors and D corresponding eigenvalues. But here, what I want to find the maximum of this one. This just tells you that, okay, it is a eigenvector, it is a eigenvalue. But which one? I totally have D eigenvectors and a D corresponding eigenvalues, right? So how can we have this? Then let's have a look at the objective function again. My objective function equal to this. And, and did you find something interesting? Which is, look at here. I have a ZTZV here, right? But by the KKT condition, my ZTZV must equal to what? Must equal to lambda V. In other words, the whole objective function would be in this way, lambda 1 times, actually you don't have to put a lambda 1. Let's say you just have the V's. You're going to have lambda times VTV. But the thing is here, VTV equal to 1. Why? Because VTV means the norm of the V. And then as we defined, the norm of V must be equal to 1 because it's a unit vector. And hence, my objective function directly equals to the eigenvalue. Now you see what? I have D eigenvalues to choose, and I want to maximize this objective function. That means what? I simply only need to choose the what? The biggest eigenvalue. Done. You see what I mean? Here, don't you worry, like, oh, well, what if my eigenvalue is a negative, positive, something? No, you don't worry this. Why? One thing is because ZTZ, it's a positive semi-definite. So first of all, technically, all these lambdas, must be what? If not degraded, all of them must be non-negative. And this tells me that the first PC, V1, must be the eigenvector of the ZTZ corresponding to the largest eigenvalue. So immediately I find the first PC. Then the interesting thing is, well, okay, you find the first PC, then as we define, oh, sorry, let me erase this part. As we define here, because I have D dimensions, so technically I should have D PCs. So how about the second PC, the third PC, the Dth PC? How can you find it? So similarly, here I can sort out the PCs by what? By this lambda actually. Because why? Because I define all these PCs to be orthonormal. And my eigenvectors by definition themselves are orthonormal. And hence I can naturally directly use the system, or let's say the basis of these D eigenvectors to be the basis of my PCs. Be careful that this is not okay. This is not a rigorous like mathematical derivation. This is just I happens to define this way and I find a solution. So I'm gonna say, why do I need to use my brain to think other solutions? Since already the system of eigenvectors already gave me a coordinate which satisfies all my conditions, so I can use it. But here I show a rigorous mathematical derivation that we can indeed use this one, which is the eigenvector system, to use them to be my whole PC principal component system. So if you are interested, you can, I don't believe I need it, so I can close it. If you're interested, you can just, you can just see here. I forgot which sector here. Let me sections 2.1, so that you're gonna see why this is indeed a natural derivation, which is right here. Okay, but let me skip this part. Let me directly introduce the next thing. The next thing is a concept, a definition called a score. So score is super simple, nothing but just your centered matrix Z projected onto your vector J. So Z multiply Vj gonna be a vector, right? So this vector, for each corresponding element is gonna be the score of the J's PC. So that's the thing. We will see this later in the Python coding a lot. But here, let me show you another example. I know I have introduced all these things. Let's see an example. So first of all, suppose I have 5 observed data, which means n equal to 5, and the dimension is 3D, so d equal to 3. These are this. Okay, first of all, let's calculate the mean vector. Again, v mean vector, the dimension equals to dimension of the feature. So, okay, for each feature, I should have a mean. So let's say for 4, how do I calculate 10 plus 5 plus 9 plus negative 9 plus 5 divided by 5, which is 4. So I have this x bar. Then z, how to calculate x minus x bar and then t, right? In other words, as each row, let's say 10 minus 4 equal to 6, 11 minus 0.4 equal to 10.6, and vice versa, no, vice versa. And then you just repeat it for the 4 vectors, means 5 vectors means the 5 observed data. You have this z. Okay, then I can calculate ztz. Sorry about it. Okay, I can calculate the eigenvalues of the ztz matrix. The eigenvalues are here. These 3 numbers. Let me just underline this. These 3 numbers. And then the corresponding eigenvectors are these 3 respectively. Okay, now let me ask you, which one should be my first principal component, the first PC? We're gonna see the biggest eigenvalue, right? Why? Because as we mentioned, this one, to maximize this objective function, the objective function happens to be the eigenvalue. And hence here, and hence here, I realize I just skipped one slide. No worry, let's first calculate this part first. And hence here, 468 is the biggest eigenvalue. The corresponding eigenvector is this one. And hence I take this V1, this one to be V1, to be my eigenvector. So sorry, this eigenvector to be my first principal component. Okay, now how about the second one? Well, we see the second largest eigenvalue is this number, and hence the purple one, the purple eigenvector gonna be my V2, meaning the second PC. And then of course this is the smallest one, and then this one I even forgot. And then this one. So I use the colors, to make it a corresponding thing, to make it so this color is corresponding to this eigenvector, this color. So this is gonna be V3. Okay, now I have V1, V2, V3. And we're all talking about PCA is for dimensional reduction. But here, original is 3D. So I still have V1, V2, V3. There's no reductions at all. How can we reduce it? What is the standard? Well, what is how can we reduce it? What is the standard? Well, which is the standard for me to reduce? Okay, here we go. We need to do some further calculations. So the total variance here is nothing, just summation of all the lambdas. And by because the lambdas are because these are my eigenvectors, so that VZ is what is actually the corresponding to eigen. Give me 1 second. Why I feel I should have a square? Give me 1 second. Give me 1 second. I realize here should be. Let me see. No, there's no square. Sorry, there's no, because this directly gives this already. I can have this part. I can have. Give me 1 second. ZTZ is VV lambda V. Yes, because VV they kind of eliminate themselves, so that here I directly have the lambda J. So this is the summation. This is the total, okay? Total variance. Okay, now let's consider that I'm gonna use the first K pieces. So you may ask, why the first K pieces? Why not I just run like take 2 K pieces? This is because by definition of my first PC, this is the largest lambda already. In other words, this should explain my data the most. And hence I sort it and I can say the biggest case. Okay, then it's gonna be like here. So the difference that here for the total variance, your J is gonna summation for all the dimensions. But here for the first K, the J is gonna summation from 1 to only K. Be careful, this K must be less than or equal to D, okay? So which is called explained variance. Then how can I determine how many PCs gonna be needed to make it adequate to explain the original data. So we can calculate the ratio of the explained variance. So it's gonna be, well, you are gonna have the variance, for the first k, which is here, divided by the total variance, which is the variance of all the dimensions. I will calculate this ratio. In other words, I'm gonna ask, hey, how many percentage of the variance are explained? And then I will compare this RK with a user-defined threshold alpha. If RK is bigger than alpha, then I'm gonna say, okay, I'm gonna choose the smallest k that satisfied RK greater than or equal to alpha. It's like the confidence level, in statistics. So this, let's say, suppose my R alpha equal to 80%, and my RK is, let's say, 79%. Then I know, no, it's not enough. I need to consider the next PC. Then the next PC, suppose it is, let's say, 81%. Then 81% is greater than 80%. Then I can say, yes, here's the thing. Let's go back to this data. So first of all, I set up my alpha to be 90%. I need 90% of the variance to be explained. So now you see, I already have the first PC, the eigenvalue is 486. The second PC eigenvalue is 161. The third one, again, it should be from the biggest number to the smallest number. It's a descending, order. And then the last one, this one. So I'm gonna see, first of all, what is my R1? R1 means I only use my first principal component. So the corresponding, let me see, explained variance divided by the total variance, variance, which is 74%. But my alpha is 90%. 74% is less than 90%. That means it's not enough. Okay, now I need to add consider one more principal component. Now I have R2. R2 means I consider both PC1 and PC2. So I have this plus this over the total variance. Now I have 99.36. So this number is bigger than 90. So I will immediately stop here. In other words, to get 90% of explained variance, I only need 2 PCs. You see? Here, choose the smallest k that satisfied RK is greater than or equal to alpha. K equal to 1, not satisfied. K equal to 2, satisfied. And hence, K equal to 2 is the thing we need. In other words, we only need 2 PCs. So now, yeah, in other words, I reduce the dimension of the original data from 3D to 2D now. And also, if alpha equal to 70%, now then I only need what? I only need 1 PC, because the first PC is already 74, bigger than 70%. So that's the thing. Okay, due to the time limit, I'm gonna stop here. In the next class, we will see how can we code it, make everything, and we can see something interesting. Which is, let's say for this PC, we actually need a very little dimension of data. We can see the big difference already. And another thing is the famous face recognition. Okay, so we'll formally mention everything in the next class. And that's everything about today's class. And see you later. Have a good night. Bye-bye.